So this video, we're going to look at Dalton's law and mole fractions. And we're going to start with our gas simulation again, and we'll do some calculations in a little bit. But let's say I have some heavy particles. So I'm going to put in 20 heavy particles here. And we can see the heavy particles are out here, they're moving around, and my pressure is going to be about 2.5 atmospheres. Okay. Now, what if I go ahead and take those away and I add some light particles? Let's say I have 50 light particles. So 50 light particles, and it's about 5.5 to 6 atmospheres. So the question now is, if I take the heavy particles and the light particles and I put them all together, what's my total pressure going to be? And the answer is not that difficult, because if I take the 2.5 atmospheres from the heavy particles and the 6 atmospheres from the light particles, and you add them together, it's going to be about 8 to 8.5 atmospheres, which is what we see happening here. So Dalton's law just says I'm going to take whatever pressures the gases individually have and add them up. And those are called partial pressures. So the partial pressure of the heavy particles was 2.5 atmospheres, and the partial pressure of the light particles, which is about 6 atmospheres, and then the total pressure is the sum of the partial pressures. So the first example we had was a heavy gas, which was 2.5 atmospheres and 20 particles. And the light gas was about 6 atmospheres and 50 particles. And so what we want to be able to do is see what the total pressure is and something called partial pressure. So the partial pressure of a gas is, let's say, for instance, the heavy gas. We just call this P heavy. So P is the partial pressure, and that is 2.5 atmospheres. Okay. And if I have another gas in there, light gas, we say the partial pressure of the light gas is 6 atmospheres. So Dalton's law just says that the partial pressure of the heavy and the partial pressure of the light, if I just add them up, that's going to give me the total pressure inside the container. So if I have gases and a bunch of different things are in there and they all have different amounts in there, and I just add those up, that's going to give me total pressure. So in this case, 2.5 atmospheres plus 6 atmospheres gives me 8.5 atmospheres, and that's going to be the total pressure of the container. Okay, so this is Dalton's law, and on your equation sheet, it just says the sum of the partial pressures is going to equal the total pressure inside that container. Now, another thing that we can do with this is we can see partial pressure is related to what we call the mole fraction of the gas. So the mole fraction here, this right here, is X, and that is the moles of A over total moles. Now, I don't have moles here. I have some particles, I have the atmospheres, but if you take a look at this equation, you can see that moles and particles are related. So moles and pressure are related. So if I just go with P heavy, let's just look at the heavy one, is equal to P total times X heavy, which is the mole fraction. And I want to get mole fraction of X. Sorry, mole fraction of heavy. So X heavy is, that's just going to be pH over P total, which is 2.5 atmospheres over the total pressure, which is 8.5. So I'm just taking a fraction, whatever fraction of gas that's in there, and that's going to equal, if I divide that out, 0.294. Okay. Now you might say, well, I also have the particles of each, right? So this is, up here I have the particles. And could we do the same thing for the particles? And the answer is yes, we can. And actually, the mole fraction is the particles. So if I try that again with the X heavy, let's try the moles of H over the total moles. So that's going to be 20 over 70 total particles, because 20 plus 50 is 70. And if I do that math and I divide that out, 20 divided by 70 is 0.286, which is pretty close. These two numbers are pretty close. If you remember, the simulation is not perfect. The atmosphere is bouncing around quite a bit. And so they should be the same in theory, and they are pretty close. Okay? So this is my mole fraction. I'm just going to use the pressures this time. If I want to do the same thing with the mole fraction of, if I want to get the mole fraction of the light particles, that's just going to be the partial pressure of the light divided by the total pressure. And that's going to be 6 atmospheres over 8.5 atmospheres. And that ends up being 0.706, which is, if I take this number and this number, add them up, equals 1. So they should equal 1. All my mole fractions should equal 1 because, you know, it's all part of that substance. So let's say we have this gas mixture now, and I have a total pressure of about 11 atmospheres. You can see it's moving around a little bit, but my total pressure is about 11 atmospheres. And I want to figure out what the partial pressure of each of my gases is. So I have in here 30 heavy particles, and I have 60 light particles, giving me a total of 90 particles. Okay, let's just say that the particles, instead of 30 and 60, I'm going to use 0.30 moles of heavy and 0.60 moles of light. And the question now is, can I figure out what my partial pressures of each of these gases is? And so to do this, we have to do something called mole fractions. And the total amount is the 0.90 moles of gas. And if I want to figure out, well, what's my mole fraction of heavy and what's my mole fraction of light, and how can I use that to figure out my partial pressure, that's what we're going to do now. So here's the calculations. Okay, my second example, I had the total pressure was 11 atmospheres, and I pumped in 30 heavy particles and 60 light particles. And now I want to find out what is my partial pressure of the heavy and what is my partial pressure of the light. Okay. And so this is kind of working backwards from what we just did. I know that these two things added up have to be 11. But what we can do now is, since we have the moles here, we can go ahead and figure out what are the mole fractions of each of these and go and solve my partial pressures that way. So let's go ahead and do that. As I said in the video, instead of 30 and 60, because these are pretty big numbers and that's a lot of moles, we're going to make it 0.30, so 0.30 and 0.60. So my total is going to be 0.90 moles of gas. So these are moles of gas, of heavy, moles of light, okay? So how do I get mole fractions from these? Well, remember, mole fractions, X is going to be the moles of the heavy over the total moles. So in this case, it's 0.30 divided by 0.90, which is 0.333 repeating, okay? And that's my mole fraction. Same with mole fraction of light. Well, that's the moles of the light over the moles total. And that's going to give me 0.60 over 0.90, which is 0.667 repeating. I'll just round it. Okay, so those are my mole fractions of each of these things. Well, how do I get the partial pressures now? I have the total pressure, okay? So if you look at the equation sheet, the partial pressure of one thing is the total pressure times the mole fraction. So if I want the partial pressure of H, let's say I have partial pressure of H, that's going to be the total pressure times X of H. Okay, so that's going to equal 11.0 atmospheres times my mole fraction, which is 0.333, and that ends up being, what is that? 3.663 atmospheres. Okay. Do the same thing for partial pressure L. There's a couple ways of doing this now, because if I know H, I can get partial pressure of L by just, subtracting. So I could say, well, it's my total pressure minus partial pressure of H. So that's 11 minus 3.663. And that's going to equal 7.337 atmospheres. Okay, so that's one way of doing it. So now I have this number here and this number here, because they have to add up to be the same. Or I could just solve it the way I did up here. And you can see if I go partial pressure of L equals 11 atmospheres times my mole fraction of L, so that's 0.667. And if I do that math, that also ends up with 7.337, which is the same as what I got here. So there's multiple ways of doing this. Like I said, just get comfortable with Dalton's law and mole fractions for these types of problems.